There you go. Right, cool. Okay. So, third one. Let's have a quick recap of where we are. So, in this lecture, we're going to have a recap of where we are. We're going to... So last week I spoke about crossover distortion and how we can sort of negate that using the feedback of an op-amp. But if you remember, it doesn't completely eliminate the distortion. There's still a little bit left. So we'll go through how we can essentially eliminate that. And then the kind of like bulk of the lesson is going to be in... I'm going to go through... So what I've done, I'm going to go through two devices. We're going to make another two devices this week because we made four. I think we made four last week. And it's just a lot of information to get in. So what I've already done is I've uploaded another video to my YouTube channel. And it's a supplement to this class. So it's an hour long, or it's just over an hour long, of me making another 4 devices that you need for this schematic. I didn't want to do that here because it's too much of the same thing. But there's some skills in the supplemental video that I haven't shown in this one, or that I'm not going to demonstrate. However, if we finish a bit early and you want me to make like one of the complex devices in the next 4 that you want to make for schematic, I'll do that at the end. But that'll be kind of down to you if you want to do that. And then at the end, the last thing we'll do is the schematics. So we're actually going to get started on the schematics today. Finally, which will be good. Right, so this is where we ideally want to be with the schematics. If you're playing along, fine. If you're not, fine. It's completely your choice. So at the moment, we have these devices in there. If I can get this laser pointer thing on. All of these should be fully made components now. So they should have the correct pins, they should have the correct footprints, and I've circled this J1 over here because that one doesn't have any modification to it whatsoever. If you remember, we're only using that as a PCB feature to connect the battery wires to. So that can just be straight out of the libraries, Proteus libraries. I'd like to make one correction to the things that we did last week. So, and that is I'd like to change the packages for the linear regulators. The linear regulators that I chose last week were the through hole type that, you know, like I think the TO220 package. It's a 3 legs square thing with a tab on the back for the heatsink, sticks off the board. Everything else on this board is surface mount. So it's more in keeping to not have 2 horrendous, voltage regulators sticking off the board. Who wants that? So this will be like a neat little PCB when it's done. So, and it's relatively. So what I've basically said here, when you look on the data sheet of these 2 regulators, they come in this D2 package. What that is a TO263 package with the pins altered. So it's actually well easy to create the new package. So that's just a hint on how to do that. Right, so Class B crossover distortion stuff. Quick recap. Circuit on the left. That's Class B amplifier. That's a Class B amplifier with the feedback inside the loop of the op-amp, meaning that the op-amp is correcting for the errors of these 2 current gain transistors. Problem with that, and I mentioned it just before, is that for the vast majority of the time it's okay, but if you kind of like zoom into this little tiny region here, you can see that the op-amps can't do the entire job of eliminating crossover distortion. So what can we do? So I hinted at this last week. This is a new amplifier topology that you may or may have not seen before. It's very common, it's just I have not spoken about it yet in this series. And it's called Class AB Amplification. Now, what's the difference here in this circuit? Correct. Not quite in the feedback though, because if you see where I've put the feedback of that op-amp, they create 2 offsets going to the bases of these transistors. Can anyone guess? I'm going to choose this tool here. highlighter, pen? Yeah. So can anybody guess if the waveform here, right, looks like this, what's the waveform here going to look like?
Increased by whatever that voltage is.
Is it going to be offset? Offset by 700?
Exactly.
Which direction?
Ah, okay. Yeah.
Yes. So, I'll tell you what, I'll do this in a different colour. Choose that. Oh, good. And then, who can guess what the other side is?
The opposite.
Yeah.
Negative offset.
What's that going to do to the transistors?
Value crossover distortion.
But why? What's...
Because it's overcoming the 0.7 junction.
Yes.
The B junction.
Yeah, exactly. So, if we could buy batteries that are 700 millivolts and last an infinite amount of time, then you'd put a couple of 700 millivolt batteries there and you'd overcome crossover distortion entirely. Because these two transistors, the NPN and the PNP transistors, have been biased on. So they're now on ever so slightly at the 0 point, at the quiescent point, when there's 0 voltage coming in. So, okay, that's cool. So how do we do that sort of practically? So what I'm going to do is I'm actually going to show you a very quick simulation.
Class AB.
That's called Class AB.
Okay. I see, yeah.
The reason why it's called Class AB is because Class A amplifiers are single transistor devices. They only work in the positive region or the negative region if you use a PNP, and they're biased halfway between the rails. They're not even biased at 0 point. They're biased between halfway between V++ and ground. They're always on, and they burn energy. However, you've got excellent linearity because you don't have to deal with crossover distortion. It's a big trade-off. Class AB is biasing those two transistors on a little bit so that you overcome that crossover distortion.
More energy efficient.
It's more energy efficient. Can we see that? We can. Right. So this is Tina TI. This is a program that I really like to use for simulations because I've got quite used to it, and it's quick and easy, and some of the tools that you can use to analyze your circuits are really good and intuitive to use. You can do complicated stuff like noise analysis and stability analysis and stuff of op-amp circuits. So this is your Class B amplifier, okay? You can tell that. I've got it configured as a buffer. It doesn't really matter. If it was an amplifier, you would have a resistor in the feedback and a resistor here to ground. But it's kind of irrelevant. For what we're viewing here, we're just interested in the Class B operation of this thing. So what I'm going to do, if I remember the shortcut, I'm going to do transient analysis for 2 milliseconds, right? Just a couple of notes here. I've got V in at the bottom. That's our audio source. I've got this and this. Can anyone guess what these are? Yes. So I'm measuring the current through that transistor, and I'm measuring the current through this transistor. And then I've got a V out here, so I'm measuring the output voltage as well. Cool. Right, so when I hover over a trace, can you see on the bottom, can you see this thing here? That changes, that tells you, it says that V out there, and then there it says V in, so you can see which trace I'm looking at. So we can see that the input voltage is a perfectly clean sinusoidal, and when you can see the output voltage has got this horrendous crossover distortion. I've made this circuit so that it exaggerates this problem. But as you turn the volume down, for example, you'll start to experience the crossover distortion more, because the crossover distortion is an absolute voltage at 0.7 volts. If that's swamped within a 1,000 volt amplifier signal, you won't hear it. If it's in a 1 volt signal, it's mostly distortion. So that's, you can see that. So I'm going to delete both of these traces, and I'm going to re-zoom into these. Now, you can see this trace, that highlights red, that's your NPN current thingy. So that's your current trace going through the NPN transistor, clearly showing that there's a dead zone. And then the PNP transistor, that's a current going through there as well. One thing I'd like to note at this point is if I take a measurement, so you see this A thing that I'm dragging, you see that it follows that trace. That's showing you the voltage. So this is the y-axis and this is the x-axis, so time and voltage. So if I do it at the point where it's meant to be off, you can see that we're down to like minus 300 picovolts. So that's just like either slight capacitances, leakages of the transistor, that kind of thing. So this transistor really is off. There's literally no current going through it. Just wanted to make that point at this moment. So let's have a look at this one. 50. So here, it's exactly the same circuit, but I've got the feedback loop within these two transistors. See? Right. Bear in mind, I've not got the ammeter. I've not got the ammeters in these in the transistor path, but we can see that it does a much better job. Not only does it reduce the crossover distortion at these low amplitudes, but it also has brought the voltage up to exactly what the demand signal is coming in, and that's because the op amp is now compensating for the any voltage drops within those transistors as well. So if I just quickly illustrate here, you can see the crossover distortion that we're talking about. It's still there. So then we're going to go over to the one that we're going to be building, which is this. So feedback loop's still local. However, I've got this biasing network. You can bias these transistors with resistors. Problem with that is that the resistors get hot and cold and you change the bias points quite easily. I've got two diodes here that create a 0.7 volt offset, and that will bias these transistors to 0.7 volts. So if we just take a quick look at that now. Because we're not compensating for the slight drops in voltage, we still get a slightly lower wave, lower amplitude, but you can see the crossover distortion is essentially eliminated. That's the output, this is the input. If I show the current traces, zoom into that, you can see that slight change in current trace now, you've biased them both on slightly, especially when the input voltage starts to trend towards zero. And that thing that I said about them being completely off, so as the voltage trends towards zero, you can see we're now at 11 microvolts. That's a lot more than, a few picovolts. So these things are actually turning on quicker. So, cool, right. I am going to get back to this. Excellent. Right, so like I said before, instead of me going through a whole, bunch of devices to make them in Proteus again, I've already made a supplemental video where I'm going to go through the rest of these, so you can kind of do it at your own pace, and you're not just being inundated with the same thing over and over again, because I wouldn't be able to concentrate in that situation. So I don't know how, it would be silly to ask anybody to do that. So, yeah.
The AB amplifier.
Yeah.
Is it used for the feedback as well?
Well, not usually. However, the circuit that we're going to make will have that option to do that. So, as another thing, I'll either I'll explore that option next week, or we'll explore it when we've got the circuits together. You'll be able to then have AB amp with compensation on the op amp, and then you can see what that does. So, don't know. I don't know. AB amp with op amp compensation. But no, it's not a different topology. Yeah. Sorry, it's not a different topology. All the other amplifier topologies are just, they're completely different to this now. So, the devices that we aren't going to cover today, there's a DC-DC converter that needs to be added. This takes in 9 to 18 volts and outputs a plus minus 15 volt rail. An LED, so that you know when things on. A volume potentiometer with switch. So this is quite an interesting one. So you know those potentiometers that you can turn completely counterclockwise, and then there's a click. That's what we're going to use. So we'll be able to turn the circuit on and off with that little switch. Notice that it says log here. Why does it say log? Does anyone know? Logarithmic. So why do we want logarithmic? Why? Yeah, and why?
Decibels are a logarithmic scale.
Decibels are, but how does that relate to our perception of audio? If you know.
It'll be smooth to the ear, basically. You know, as you're listening to it.
Yeah.
It's not going to be abrupt when you're on or off.
Yeah.
It's going to fade out.
Does anyone hear that? Okay, so what that is essentially is the logarithmic scale and the decibel scale. Our ears are more sensitive to small changes in loudness at lower volumes than they are at higher volumes. So if you're like blasting music out and you want even more volume, you have to put a lot more power in for the perception of audio to get louder. If you're listening to something absolutely tiny, being really quiet, and you turn the audio up a tiny bit, it'll be like, oh, it's too loud. You know, so that's why we use logarithmic. So that when you change the dial, you get that perception of linear audio change, where it's not actually in reality you're going up, 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 up as you get louder. And then we've got a voltage input jack, a DC input jack. Yeah. So, first thing we're going to do is create a generic resistor, because we didn't do that last week. We're going to make one resistor that you'll then be able to just throw at all your schematics until you need a resistor that's like well specific, that's got high power capability, or it's like 0.001% accurate. You can use this generic resistor. So let's do that. So this will be one of the easiest ones that you ever make. So first thing is we're going to pick any old resistor out of the Proteus library. Let's choose not an NTC. Let's not choose that. Generic resistor symbol, that'll do. Okay, place a resistor, and then I'm going to, what am I going to do? I will simply right click and make device. I don't even need to decompose it. I can just simply right click make device and make the device on top of this. I'm going to call it resistor generic. I'm going to call it 1% because the tolerance, we're going to make specifically toleranced resistors. And then it's going to have various different packages we can choose as well, so I'm just going to keep it like that. Okay, this already came with all of the packages. So I've chosen one that comes with all the packages anyway. So what I was going to do at that point was add here 0603. Did it come with 0402?
I think so.
It did. Oh yeah, it did. Right. Well, yeah. The four packages were going to be 0402, 0603, 0805, and then 1210. They would cover all the sizes you need. But if you choose that resistor generic, you'll get this as well. So that's absolutely fine. Assign the package, click next. Value, we're going to just keep it as 10K. You'll change that as you use it. Prim type, we don't need that or that. So we've just got two properties to this thing at the moment. And then I'm going to put it into our resistor thing, our resistor library. Delete the one on schematic and place the one that's in your library. Now, we do need to do the custom component script thing. So I've sent you all this file. This, I'll show you. You don't actually need that, but it makes it quicker. I'll show you why I don't need it. If I do make device, I go next, next. You can actually add all of those fields one by one here, if you want. but it's a lot quicker just to stick it all in there and then make, and then you get them all. So value is going to be 10k. What is that? What? Can you tell that I'm tired? Package. Our default package is always going to be 0603. It's small, but it's not so small it's a grain of sand, and it's not you know it's good for as a starting point. Everything else is going to be not specified apart from the tolerance. We're going to keep it 1%. That's plus minus 1%. You should always specify that.
You can just specify the power.
It very much depends what the package you choose. So if you're picking a generic resistor, you're kind of assuming that within certain parameters it's not going to be a high-powered resistor. If you know that a certain resistor in your circuit is going to require a bit more power, then you can put the power in there. And also then you'd specify a slightly larger package, probably. But for signal level stuff, you can leave that.
What's the default power in these packages? Is it 1/4 of a watt? Is this 250?
Yeah, I believe so. I actually don't know.
Yeah, 603 is a
Quarter of a watt. Yeah.
I think probably 6.5.
Yeah. Yeah. Generic, yes, it is. And then we can literally just remake that, save it, done. Save it in the library. Then we essentially got a generic resistor to use. Now, if we want to use higher tolerance parts, what I tend to do is just create one more, which is 0% one, so 0.1%. You can just make the exact same resistor, and all you need to do is change the name of it in the library and change the value here in its properties. Click next, 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 and then now you've got 1% resistors to use. You've got 0.1% resistors to use, and you can just chuck them at your schematics now. You don't have to like pick a specific device for every single one you use. That saves quite a lot of time.
Would you not want that on the label as well then? Like the tolerance, if you've got more than one, so that you can quickly see.
Do you mean?
Like on there, like 1% beside it, and then.
You mean here?
Yeah, is that an advantage? Not really.
You don't usually have your tolerance on your schematic, specified in your schematic. You can if you want. It's up to you. But
just thinking like from a point of view of, if you.
A glance on the schematic.
Yeah.
You could. It's completely up to you. What I tend to do is just keep it in the properties, and then in the bill of materials,
Oh, that's the important one.
the bill of materials will tell you that that's a 0.1% device.
In your name, can you not use a decimal point? So
Okay, so in the value that appears on the schematic, you can. In the library name, these are the library names that you simply search in a library. No, because when you do, I'll show you. Make device. If I put a dot there, Proteus will warn me at some point. Contains a dot character. There's a special meaning in that all devices to the left with the something, blah, blah. So I just avoid it. Yeah, so it's a special character within Proteus. It's treated specially, so that's why you can't do it. Cool, right, so I'm going to do one more. And, well, I say you are going to do one more. So I'm just going to be a robot that'll just do what you tell me to do now. So over to you guys. I'm going to open this thing on Farnell. Just give me 2 seconds. Open that. And so the device is a Schottky diode. Farnell's working this week, which is good. And I want to place this on the schematic, and I'm going to use it as protection to stop power supplies fighting each other. So what do I do? What is the first step? That's not a bad first step, is it? Let's check the data sheet. Okay.
Go back to Proteus.
Go back to Proteus.
And search for a generic shot.
Okay. Okie dokie. That always opens on the other screen. Schottky. Do you want that?
No.
Do you want that?
You'll probably find a package number in the data sheet, potentially.
We're going to check that anyway. But yeah, we could do.
Cool. Right, we'll use this one as a template. Oh,
Right.
I gave you too much of a hint, Linda.
Go right, click on it, properties, and then put your text in the other properties.
Okay.
Now we need to do make divides, right click make divide. Oh, that's someone else. I think.
What would you put in this bit?
In the device name, any of the relevant data sheet
Um,
elements.
You'll have to go back to the data sheet basically. There's some information.
Okay, what would we like to know about this Schottky diode?
Oh wait,
30 volts, around 2 amps.
What does that voltage there tell you about it? What's usually the headline voltage?
The breakover.
Yeah. Yeah. And 2 amps is the constant current that you can put through it, DC current. Okay, so forward voltage we can do, we will do, we'll put it in one of the properties later. Okay, so I will go back to Proteus and I'm going to call it diode.
No. Shot key diode. Or shot. Just shot.
So what I am going to do is call it or I suppose you could get rid of diode if you want, but yeah, okay. And then we are going to put those 2 headline things, shall we? So what was it? 30 volts, 2 amps. Cool. Right. Next, should I?
Yeah. Yes. Yeah.
Yeah. Cool. Oh, okay. What we're going to use is its package.
So you've got to go back and go to the
Okay. Should I find the package?
dimensions. Yeah.
Okay, so we've got this bit of information here, which is pretty cool. We've got anode, cathode, 1, 2,
One.
anode, cathode.
So now you go back to the.
Okay, we've found SC90 and we've found SOD323F. So I'll have a look in here. So I'm going to delete this one because the chance of it being right is pretty slim. I'm going to go into there. SC90. Wah. Okay. What was the other one? SOD 3, 2, 3. Wah.
Space 3.
Space 3, 2, 3. Okay. Now, should I use that? Yeah?
Well, no, we need to check the 92 and a half.
92.5 thou.
Do we
Okay,
need to check
between the
that?
pins. We definitely do need to check. So our device, if you look at the top, can you see that? PME G3020EJ. Okay?
Yeah.
So PME 302EJ, so that is our package.
Yeah.
It could have been this one. I will go to this part.
So our package is the one on the right.
Our package is one on the right, yep.
And it's in millimeters.
It's in millimeters, hooray. We come across this problem all the time, where you have to convert from thou to mils all the time. It's just the way the world is, I'm afraid. And then, oh, look what we found. We found some landing pads as well. So I'm currently in the assign packages thing. So it's going to be quite difficult for me to check this footprint at the moment. So what I'm going to do is I will make this device. Is there a problem?
We'll check that out in
We'll check. Yeah. If one's red and one's white, what does this mean?
They're not labeled properly. K is not labeled properly.
Yeah. So it's not connected. So I'm going to rename. What should I put here?
Okay.
There you go. That's connected.
And that is the right distance between the pads. I just checked it.
Okay.
That is right.
Excellent. Okay. Right.
2.3 is just less than 2 point whatever it was. It's just more than so.
Right. Okay. Right. I'll demonstrate that in the layout section as well. So the value of this part, I'm just gonna call it. It's a manufacturer's part number. So that'll appear on the schematic. 1, 2, 3, 4. Voltage was 30 volts.
Yeah.
The current was 2 amps, I think, was it?
Yeah.
Yeah, cool, thank you. The power you can get from the data sheet. I'm doing this in the just to be fast about it. Manufacturer, Nexperia. Manufacturer's part number, I did copy it, here you go. Stockist is, now. Stockist part number is, double click that and it will copy, should do. Special VF, this is what you were saying, Doomy. So I usually do put the VF figure in the special part of diodes because it's another critical.
Does that move the top down first page?
Yeah, so we've actually got this table here. So really, you want to kind of choose the worst case scenario, which will be 620 millivolts in this case. Whoa, what unit's that? And it's not generic. Okay, so I'm going to finish off this part. That's left over from the previous part that I used. Yeah. Oh, did I? 50. Yeah, thank you. And then it's going. Which library is it going in? Semi. And it's not from DigiKey. It's not that part either, so I'll just get rid of that. Right. Delete that one. Place this new one. That's our new part. So let's place D2, get rid of that board outline because we don't need it. Place D2 on this board. So I'm going to go to this component mode tool, and then D2 is there. Place it on the board. Now we've got our package that we can sort of inspect. I've placed a false origin. Did I explain false origins? If you press O somewhere on the layout, it places this kind of thing. That's where your new reference point is when you're taking measurements. And you can tell whether you've got a false origin placed because this purple text on the bottom right there. So if you put your false origin on one of the pins, you don't necessarily have to do this at this stage, but you can measure the distance between these two, the center of these two, quite easily. And that's 2.349 millimeters. I saw that down here. If you look again, 2.349. If you press M, it changes the grid from metric to imperial. So that's an imperial because it says thou in the bottom right corner. That's millimeters. So in thou, that was 92.5, which was the what it said in the package thing before. Now, I will explain this bit. So we've got a package outline and dimensions and stuff, and we've got these dimensions in millimeters. We've also got a recommended footprint. That's for the 123. This is for the 323F. The recommended footprint, we can have a look. So it tells you where the solder lands are, where the copper is, solder resist, occupied area, and solder paste. At the moment, we're just going to look at the lands and just make sure that the lands are okay. That's where the actual copper squares are. And that is this slightly thicker square. So you can see that we've got 1.6 mil between one end and the other end, and then we've got 2.8 mil between the other two. So I shouldn't really be doing this, but what was that? 1.6. This is going to be negative, but it doesn't matter. 1.2. So that tells us the. What does that tell us?
If we down divide that in two, that would be our pad width.
Yeah, correct.
So it's 0.6.
Yeah,
which is
0.6.
fine, which is just a little bit more than the inner square, which is measuring at 0.5.
Yeah.
So maybe that makes sense.
And then actually you've got that measurement here as well.
Oh, yeah.
Okay, so we've got 0.6 by, well, it's going to be 0.6 by 0.6. That pad is actually a bit off. It looks a bit off. There are other pads, there are other footprints that you can use in the Proteus library. So if you noticed when we searched before, if I search for small outline diode, SOD, you've got these IPC footprints as well. Now, you can, there's quite a few little variations on these footprints that you can choose from. And I would...
Whoa, hang on, Dan, that's all about millimetres. Is that because you've got your thing in millimetres?
Yeah, I think it is.
So that could help.
Actually, sorry. We're in thou still.
Okay.
You're right, though. I've never noticed that before.
Okay.
I've never noticed that.
If we're struggling with a data sheet, go back to this, change this to millimetres or thou, whichever one.
Well, it's in thou at the moment, because it says at the bottom.
Oh,
So if I change that to millimetres,
what happens with these then?
yeah, I will go to package mode. I'll select the SO small. SOD 2 mil. Is it the? I think it might be the okay. I think it might be the package specific. What was the package that we were looking at? 323. Thank you. Oh, it was there at the top of the list. Yeah,
Okay.
it's down to the package and what that package was made in at the time. Yeah. Okay. So what I'm going to do is I'm going to attempt to find an IPC footprint that's closer to the device that we're going to make. And the way that we can do that is by, I mean, initially you can look at the information that you get in here. So you see the description, you've got 0.85 millimeters width, 1.25 millimeters length, 0.65 millimeters body, and it also gives you the distance between pads, the center points of the pads. So if we go back to our device and we have a look at the actual body of the device, we've got 1.35, it could be down to 1.15, but we'll take that, and then about 1.7. So we've got 1.35. These are all very, very close. Can you see 1.35, 1.37? They're all extremely close. And then we've got 1.8, 1.8, 1.77. Again, these are all extremely close. And if you have a look at the actual footprints themselves down here in the bottom left, there's barely any difference whatsoever. So it's looking like these would be quite appropriate to use. The distance between the edge of the pins is between 2.3 and 2.7. Between our pads, we've got 2.6, so we can be pretty sure that those pins are going to land on those pads perfectly. So, last thing we can do is check the height of the package, and I'm pretty sure the height of this is, so that's 0.8, so it's actually shorter than both of these here. So I'm going to go for the shortest one. So that one will actually fit better than the one that comes, the one that you think would fit. That's why it's important to check your footprints and to actually check the dimensions of the part that you're placing, because it might say that there's something in the library, but when you actually come down to check it, the reality is you'll buy the PCB, you'll buy the component, you'll solder it, and you'll be like, it doesn't fit. Right, so I'm going to copy the name of that package, and I'm going to go into Schematic capture, and I'm going to go into there, and I'm going to stick it into this PCB package thing. I'm going to right click it, make device, and I'm going to go next, 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 next. Okay, yes, close, place it, package. Right, That's it. So that is our that's our Schottky diode. Now what I'm going to do is I'm going to skip ahead now, and I'm going to get to the schematic side, because nobody wants to watch any more devices being made. So what I'm going to do is go into here. I'm going to open and hope that this is the right one. Don't need this anymore. Right, so these are all the components that you'll need to make this amplifier. The ones that I haven't demonstrated to you so far, this thing, that's the switch potentiometer thing. It's a bit more of a complicated device. Again, it's in the video, the supplementary video that I made, so you can see how that's made there, or I can demonstrate it at the very end. The other thing, this DC barrel jack. So both that device and this one are made by placing a switch and placing a potentiometer, breaking the two devices by decomposing them, and taking those the images and sticking them together and then making one device out of it. This thing, I just drew. So you can just draw stuff. So I just drew this. And when you're drawing stuff, you can use sort of any grid you want, really, so long as your 3 pins line up on the 0.1 inch grid pitch. We should always make our schematics in 0.1 inch. That means that when you swap it and give it to somebody else, all the grids will align, everything will align, it'll look nice, it'll be proper. When you're making devices, you can use features that are smaller, but make sure that all your pins eventually line up on the 0.1 inch grid, like that. So I'm not showing you that, I'm not showing you the one. I didn't show the LED, but it's pretty straightforward. In fact, I'll quickly show you the package for that. So I go into here, and then I can place a component called D1. So that is an 0603 package, but it's now got polarity. So I've put the bar there for the cathode of the LED, and I've got a dot to indicate the cathode as well. When you go in the data sheet, you'll see that there's a dot on the actual tiny SMD LED as well. So that's why I've put that there. And then there was this thing I've not shown you either. This is the switch mode power supply, where it takes 9 to 18 volts in here, and then it outputs plus 15, 0, minus 15 that we can use as our rails. Right, so let's start drawing a schematic. Few things to know. Let's start with power. No, let's start with input. So our power comes in through either a barrel jack or it comes in through a 9-volt connector. I'm using the Schottky diodes here as, what am I using these for?
Protection.
What do they protect from?
Anything going back.
Anything going back. So what situation could give you a bad time?
You send 9 volts down your input source.
If you had a spike in power somehow.
All plugs in both.
Yeah. So if you've got a 9-volt battery and you've got a 12-volt power supply and you're connecting together in this circuit, if you didn't have these diodes, the 12-volt supply would be connected to your 9-volt battery and well, it wouldn't pop, but you could bad things could happen. So notice here, I've right-click place and I've got terminal. So this terminal you can place default, so you can place labels. See that power in just above? That's just a default terminal. It's got nothing special about it apart from it just creates connections in the schematic. That's it. When you name it and name another one the same thing, it'll create a connection. The special ones are the ones that we're going to be interested in really is power and ground. These are treated differently within Proteus. When you place a power or you place a ground terminal, in the layout you can make a power plane from it. With the other ones you can't. So I've placed a ground terminal and I've placed it next to this connector. I'm going to connect both the switch element part and the other sleeve connector together, and I'm going to call this ground. And then we've got our input power. So I've got power in going to this label here, which I did before. Where do I want to now carry that power in?
To the chip, power device.
No,
To your tracker power supply.
no. Switch. So we'll connect this to a switch, and then the switch can then go to the this power supply over here. I've already got power in and then power switched. That SW sounds for power switched. So I'm going to click that. Plus and minus on your number pad rotates stuff. And if you want to rotate that label, go into the thing and then click horizontal here. And you can also rotate your labels if you want to do that. Right, now we've got power to this point. So I'm going to connect it to this LED to show that something's powered. I'm going to connect it to power in here. And then I'm going to place another ground net. Copy and paste is absolutely fine. And stick it there. Right, now I've got plus 15 ground and minus 15. I'm going to place terminals, power. Plus 15 volts. Minus 15 volts. And then I'm going to place a ground there as well. Like so. Right. Power. Are we done with power yet?
No fuses.
There's no fuses. I'm not going to put a fuse on it.
Yeah, I think we are. For that U3 we are.
Where else would the power go after this?
Up to 12-volt reg.
Regulators. So we're going to use a couple of regulators to regulate the switch mode power down to 12 volts. Like so. This is pretty simple stuff at this point. I've got plus 15, plus 12, and what am I going to put here?
On the other side, negative 15.
Minus 15. There. I'm going to put a minus 15 here and make sure I change it, because otherwise that'll be rubbish. Say again?
Just a small bugbear of people do the four into one junction, because it's really easy to miss when you've not done it properly.
Yes, I know about that. There are the original reason for that was I think it was for photocopying. You couldn't really see the center point.
Yeah. Well, it's more, it's when I've done it before and I've got a line going through and I thought it's connected, but because it's got another junction on there already.
Yes.
So you think it's connected, it's not. So
Yeah.
Just a personal thing, but I was like making it
Offset.
only ever 3 into one junction.
Yeah. Now, what Joe's talking about there, if you didn't follow along, is offsetting the ground slightly, so that if that went through, if for some reason this trace went, I can't do it at that point, but it's because this device is in the way. But for example, you could have that there, this trace could go through. Oh, it doesn't do it. I think Proteus stops that from happening. But the point is that in some packages, you could think that something's connected because you put a wire through and it's not. So the surefire way to eliminate that problem is to offset, and you only have 3 connections to one junction.
Well, that doesn't look pretty.
I know, that's why I don't like it.
So I would then put my ground on the very right-hand corner.
Yes, yeah. That would be a nice way to do it.
And then it'll
Yeah.
still look pretty.
Not symmetrical.
I'm just going to put that there just to. It's gross, isn't it? Everyone hates it.
Never gonna work. Oh.
Yeah,
That's it, I'm
just
not
broke the
coming
whole
back.
circuit. Yeah, cool. Right, so what have we got? We've got 15, 12, 15, 12. Now, can we put that onto our circuit?
Yeah.
Yes, we can. Right, let's take it over here. Plus 15. Plus 12 minus 12. I'm just copy and pasting these over here just because it's easier. So we've got the switch thing here. I'm going to take okay, we haven't got audio to this device yet, so power's there, but let's just get our audio signals in so that the last thing that we do is this. So we've got these 2 jacks. I'm going to place default terminals. You can use input terminal, output terminal, bidirectional terminals if you want, but I tend to just use default terminals for simple stuff. The input terminals, output terminals, and bidirectional ones, these ones, are treated just as normal elements on the schematic anyway. So there's not, you know what I mean? There's nothing special. They're not like power planes, for example. So this is, we're going to call this one our input jack. So this is going to be R_in for right. Okay, and then we're going to have this as L_in, which is left. And I'm going to take these two signals. Now I've got audio, which is good. We want that. I'm going to put them here. And I'm going to make the left channel at the top. So rotate that. And then where do I stick the, I'm kind of giving it away by where I put it. Where do I connect this thing to? So again, percent geometer, which terminal? The lower one.
Yeah.
If I connect this, when you turn the knob counterclockwise, you have to use your mind's eye to imagine this. You turn it counterclockwise, the wiper,
No, sorry, the top channel.
yeah, the wiper is going to be now closer to the counterclockwise thing.
Okay.
And that'll be, you know, it'll make it lower volume. So audio goes in the top, and what goes on the bottom? Ground goes on bottom. Ground. Move that label over there. Put that on there. Put that ground. Oh yeah, if you're choosing nets, it's better to choose this drop-down menu so that you don't make a spelling mistake. You don't call like one -12 volts and another one space -12 volts or something, because then the nets aren't connected, and you'll be like, why does my circuit not work? And you'll be like, oh.
Does it take spaces afterwards as well?
I don't think spaces are ones that can be problematic. Spaces mid the thing can. Before or after, I'm not sure.
Caps make a difference.
I'll tell you now, actually. Yeah, caps will. I put a space there, so if we've got two L in, oh, it's saved it, hasn't it? L in, yeah. So it does. Yes, it absolutely does. Beware of that. What does C1 do?
AC coupling noise.
You have to make your mind up on one of them.
Gets rid of the DC.
Yeah. Yeah, exactly. AC coupling, DC blocking, two sides of the same coin. 330 nanofarads. If you're not familiar with kind of like circuits and stuff, 330 nanofarads is actually quite a small capacitor. I've chosen this small capacitor, one, because I've already used 330 nanofarads on the circuit, and if we can reuse a certain thing, it's one less thing to do. Two, the input impedance of that op-amp is very, very high, which means that the low-pass filter that a 330 nan cap and the input impedance of the op-amp to ground is going to make is very, very low. So the low-pass filter will still have a very low crossover point. So what I'm saying is you still should be able to get about a 1 hertz signal through this thing. You can't hear 1 hertz. It's way, way low enough. I think that's how it's going to work. I've not made this circuit yet. We'll find out together. Right. Now, what do I need to do to this?
So your low pass filter, so have you done some calculations to see where the cut offs are?
Yeah, it's about 1 hertz because of the input impedance of that op-amp.
Or put a feedback, sorry, feedback.
Yeah.
So the input impedance is it in mega?
Yeah. Yeah. The input impedance to these things is huge. It's got input capacitance to ground as well, but that only starts to make an effect when you get to higher frequencies. Right, why have I connected that feedback loop to J3 rather than the output of the op-amp?
So you can change the gain. Perhaps you're gonna maybe is this gonna have header?
It's going to have header pins on it, and it's also going to have a jumper rather than, yeah.
So you can switch the jumper.
Yes, I can switch the jumper. So it's not to change the gain, it's to change the topology of the circuit. So remember, when we'll be able to change this, we have to change it to different configurations. So what I've done here is we're going to use little jumpers to be able to change the configuration of the op amp.
Just to go back when you say you have got your the pin 3 and 2. I mean they are like connected, isn't it? Effectively. So your filter will it not be through R3? Because that's like a virtual ground. Those two are like connected, isn't it?
That's a good point. Perhaps it will be. If it is, then the low pass filter is going to be a lot higher. The high pass filter will be a lot higher.
Then we can find out.
Yes, we will. So that potentially could have been something that I've missed. What Doom is saying there is that the op amp tries to keep these two inputs to exactly the same voltage at all times, meaning that you create a virtual. Now that isn't a virtual ground point because that's
it's a virtual connection. Basically.
it's a virtual connection to this point here, but that point is connected to ground.
Yeah.
So what he's saying is that if these are virtually connected through the op amp, then we would have a filter of 330 nanofarads and 1K, and that could create a frequency response of that amplifier that's not ideal. Now there's a very, very easy way to check that, and it's to use Tina TI and simulate it. So I'll do that. We'll do it today. And then email out. Okay, so I'm just adding the power. So it's worth noting at this point, the power is always next to the non-inverting pin, that's always positive power. I think that was done so it's easy to wire these things up.
Do you not need a coupling after that, or?
Decoupling,
Yeah.
these,
You've got rid of that.
yeah. We'll do that bit now then. So decoupling caps for these active devices are there to provide low inductance power essentially to that device. And when we come to lay out the circuit, emphasis will be made on the position of these relative to the device that they're trying to decouple as well. It's to do with frequency. It's to do with the fact that when certain devices draw a lot of current very quickly, that creates potential differences across tracks and other features that are non-desirable, mainly because of the inductance of those features. Decoupling caps help eliminate that problem.
We must always use 100 farad.
The reason, now I watched a video a few weeks ago. The reason is, traditionally, back in the day, you needed a 100 nanofarad capacitor to deal with the high frequency stuff, and then you needed a higher capacitance capacitor to deal with the low frequency stuff. Ceramic capacitors these days are so small and so good at offloading current quickly. You usually don't need those 2 or 3 different types of capacitor anymore. You can just use ceramics. 100 nanofarads is used as standard, but I think you could get away with more, is what I'm saying. I think you could put 1 microfarad capacitors here, and you'd still you wouldn't sacrifice high frequency performance. But it's also dependent on, it's actually quite dependent on the devices that you use. If this thing can draw a lot of current very quickly, perhaps 100 nanofarads wouldn't be good enough. So I think the answer is it depends on what it's connected to.
Usually the IC manufacturer will advise you as well.
They do. They put the recommended decoupling values in the data sheets, usually. So all I'm doing now is wiring up the class AB part of this circuit. Is that connecting there? Okay, so this header, I'm going to connect these 2 wires together here, these 2 pins. I'm going to connect 1 here and 1 down. I've done that 4th thing again, Joe.
Not really a problem.
Yeah.
Well, if we're going to allow it here, we go back and change it, all right?
Yeah. If I link, oh, 1 second, I just need to move this. Wire. So if this is open, this header does nothing. If I've got jumpers across pins 1 and 2 and then 3 and 4, what's going to happen?
You're going to remove your biasing
Why?
because your part is shorting out.
What am I shorting out?
Or dies.
Yeah. So I still have the resistors there, so they're still going to be.
You get the crossover distortion.
It'll return it back to Class B operation. The resistors will provide current. Now they won't at the moment because I've not added the power rails to the resistors yet. But now we can sync and source current into these power rails. So we've essentially got 10k across essentially a 24 volt rail, but that's not going to have any impact on the operation of the amplifier. It's just going to create heat. You're just going to waste energy. But since this isn't like a commercial device, this is something for us to, play with. That'll be fine in this application. So, output to the thing is here. Left in, left out. Cool. Right, so I think, now I've already done this in a different schematic, so I think that's everything on there. What I need to do now is wire up the output terminal, the output connector, left out. Ground. Change that to right. Right, so we've essentially got our amp wired up. We've only got one channel, so this would only work with the left channel at the moment. So all I'm going to do is copy and paste that entire block and put it down here. But you have to really check that your connections when you do that kind of thing, because with this whole thing's wired up for the left channel. So just and also the way that, I'll explain that afterwards actually. So firstly, I'm going to change all this to right. So you can use the drop down menus, right in, here, right out, there, and that goes there. Now you could do, if you wanted, delete this wire and put right out, get rid of that a little bit, here, to make it a little bit neater. It's up to you. It's the same thing. So the little note that I was going to make before is this device here. Now I've made this device so that when we have a look, if you go into make device and click next, the package is there, it just doesn't think it is. And we go into, actually it has to be in here. Now this is a problem with my libraries on this computer, so what I'm going to do, for some reason it's not picked it up. I'm going to go into the layout, I'm going to place RV2, because it is aware of it does have the package here, and I'm going to save this package. So I need to copy it, so it's not part of the schematic.
Oh, so you've got two wires here.
You are?
You've got two sets of resistors.
In one package.
Yes.
I didn't explain that. Yeah, exactly. Yeah.
So when you turn it, you're turning two wires simultaneously around, and that's where you've got your left and right sides.
Yes.
I was wondering.
Yes. Otherwise, you'd have two potentiometers, one for each ear, and you'd be like, I can't quite get the audio right. And it's, yeah. Yeah, you think that ground symbol's bad. Right, so all I've done here is I've saved this package into my libraries, so this should play nice now. If I click make device, next. There you go, it's appeared. So this is something I've made. I've got two gates because of that exact thing. So we've got two we've got a 2-gang potentiometer, one for left, one for right. Does it change the volume at the same time? But I've got 2 common pins here. I've got the switch 1 and switch 2 is common because I've only got 1 switch in the entire package. So that's how that's done. So essentially, the same way that you don't need to put power pins on both the common, if you've got 2 devices in one package, you don't need to put power pins on both of them in the schematic. The same thing applies to this switch. You don't have to put these 2 things here because you've already put it on this, the one at the top. And you can denote that by placing a not connected symbol. You don't have to do this if you don't want. It doesn't, Proteus doesn't care at all, but for you as the reader or designer, it might make it a little bit easier to read the schematic, to know that isn't actually used. I think that is it. Has anyone got any questions on the schematic layout side? Sorry, just the schematic side.
Is U2A meant to be U4B?
Yeah.
Ah, yes. Yeah. Good spot. Very good spot.
Because we're using the same thing.
Yeah, so that's RV1A, RV1B.
Uh-huh.
That's U4A, that's U2A. Now I've got 2 op amps, each with 2 packages on that thing. So the way to do that is you double click the second device, you change the elements, and what am I going to change it to? Yeah. And now when I press OK and go back into that menu, you can see that I've only got because I've not got 2 devices on the schematic now, it knows. So yeah, good spot.
And hence why now your pins add up, but you haven't got a repeat of 3, 2, 1. You've got
Yeah.
6, 7, 0, 0, and 3, 2, 1.
Exactly, yeah. I was only testing, that was...
Well, we passed.
You passed, flying colours. Now I'm going to delete these extra things on there. I'm going to put these here.
And is that the right thing to be doing, Dan? Because I would have thought I would leave those connected to show that still has 12 volts connected.
It's up to you.
It is a complete personal
Yeah,
preference.
yeah. What I tend to do is just leave these open. That's what I tend to do. But they are connected. You can see that it's a second gate of something because it's got colon B. It's up to you.
Can you could take a long time, adjust the second schematic so that it didn't show the power routes, couldn't you? And have
I don't know.
A 3-pin device and not a 5-pin.
Yeah, it depends on the CAN package you're using.
Yeah.
So you can do that in CAN and Albion, but
Yeah.
everything Proteus supports that.
Yes. Yeah, exactly.
Is the switch shared between left and right? Switch on the
RV1A, RV1B,
yeah.
that is shared between left and right because
So is there a way of just showing that state?
do you mean like getting rid of this on this one, for example?
Yeah.
Well, that's what these guys were saying in terms of not showing the power pins here. I don't think Proteus does support that. I've not actually gone in and tried to find that out myself, to root around.
Just 'cause, I don't know, I might have thought like there were 2 switches.
Yes, yeah, understandably. Because we've made this part and you know what that part is, you know that's, it's only got 1 switch. If you've designed this circuit, then if you've put these not connect things on there, then somebody reading it knows that those aren't connected. Now, whether they would interpret that as a second switch, they could.
But I guess I'd know as soon as it gets to the PCB layout, they'll be like, oh.
Yeah,
then it was it.
yeah. And also, you've got the part numbers in there.
Yeah.
And if you wanted to, you can go to make device and check the package and see that these 2 are common.
Yeah.
And that would also tell you that there's only 1 switch in there. But yeah, it's one thing that you just need to, with Proteus, you just have to accept that on that and understand that limitation. Any more questions on this part? We're good? Cool. Right, so let's go back to here. Done the schematics. Okay, so we've done the Proteus demo, and that is what you end up with. So what I'm going to do
You can send the link to the extra video.
Yes,
when you were saying that.
absolutely. Yeah, so I'll send a link to that as well, and that'll show you how to make those last 4 devices.
And we have all this on your, done today.
Yeah, I will do. I'll upload the lot. I won't be able to upload it today, but I will be able to upload it on Monday. I'll be able to upload it on Monday.